Thank you for having me here. This is a purely methodological paper, so I apologize in advance that there will be a little bit of math, but I'll outline the main ideas. So basically, this is a paper that tries to develop new tools for detecting selective reporting, such as p-hacking and publication bias in empirical research, and potentially provide new tools for evaluating the extent of the problem. And of course, we all know that by now, it's increasingly common that meta-analytic studies try to report some formal tests for p-hacking and publication bias in them. And what this paper offers are more powerful tools for doing so. And of course, those studies typically do this by analyzing the distributions of results published in literature, such as t-statistics and p-values. And there are two immediate challenges associated with those methods. And they're related to the fact that both null hypothesis of no selection and the alternative hypothesis of selection are highly kind of high-dimensional or composite. That comes from the fact that under the null hypothesis of no selection, we can observe different sorts of p-curves. And at the same time, there are so many different ways to p-hack the results that under the alternative, the results may look also very, very different. So this paper provides tests that are valid in the sense of controlling size over the entire set of null distributions, but at the same time quite powerful in a wide range of useful directions. So this is the most heavy slide of my presentation, but the main takeaway from the slide is that for any given study, consider a single study absent selection, for any given study, the t-statistic reported in this study can be viewed as a combination, as a sum of two major components, where the first component is the so-called local alternative, I'll call it H, and the second component will be a standard normal noise, I'll call it W. Local alternative comes from the actual effect that researchers are trying to detect, combined with the sample size and the noisiness of the observed data. And that's what determines the power of the test for a particular study. At the same time, the second component, standard normal, reflects sampling uncertainty. This structure allows us to immediately derive the power function for this particular test in this single study. However, now if we consider a literature of studies, let's say capital S studies, for each study we have some unique local alternative that comes from the fact that different studies' effects are different, sample sizes are different, sampling uncertainties are different, and those local effects in different studies imply their own t-statistics and their own p-values. Across studies, there's no reason to believe that those local effects are the same. Therefore, we think of them as being random and coming from some unknown distribution that I'll call distribution of effects. We don't know anything about the distribution, and we don't want to assume anything about this distribution. However, this assumption makes us, let us derive the distribution of p-values absent selection as kind of a functional of this unknown distribution of effects. In other words, we have a well-defined mapping between distributions of effects in a given literature and the distribution of results in the form of p-values that we are likely to observe in the absence of selection. Now, of course, this distribution may look very different depending on this distribution of effects. If all effects are very small or zeros, then we are likely to observe some sort of a uniformly distributed p-values or uniform p-curves. On the other hand, if we analyze or studies analyze very large effects, then we naturally will be observing very small p-values even under no selection. Now, formally speaking, there's an entire set of distributions in the space of p-curves that are consistent with the null hypothesis of no selection. And the formal null hypothesis that we're trying to test here is that the distribution that we observe belongs to this set. Now, what existing tests tend to do in order to test this hypothesis is deriving testable implications. Or in other words, they're kind of enlarging this null set and try to detect like an easier alternative, trying to test the easier null hypothesis. In particular, many studies focus on testing continuity. Some studies focus on testing monotonicity properties of the observed p-curve or some other upper bound properties. Now, because they're based on enlarging the null hypothesis, those tests are necessarily conservative. What I propose to do in this paper instead is observing that under the null hypothesis of no selection, assuming that's true, there is actually a way of drawing an arrow in the opposite direction from the observed distribution of p-values to the distribution of underlying effects. So it's actually possible to estimate that underlying distribution under the null hypothesis of no selection using some non-parametric techniques. But since we know, as I showed you before, the mapping that links distributions of effects to distributions of p-values, this allows us to make an extra step and estimate non-parametrically the distribution of p-values itself under the null hypothesis. So as a result, we would have access to two competing estimators of the same distribution function of p-values. One, the empirical one that is unrestricted in any way. The other one is a non-parametric one that has a null hypothesis imposed on it. Therefore, the test that I propose in the paper will be based on measures of distance between these two distributions. If these two distributions are close to each other, that probably means that there is no selection. On the other hand, if they're too far from each other, that may be because of selection. Now, to demonstrate the power properties and improvements from using this new test, I constructed these two artificial kind of forms of p-hacking. Suppose I give you two literatures represented by these histograms. I ask you which one is p-hacked. The true answer is both of them are p-hacked, and the fraction of results reported selectively in those literatures are identical and equal to 50%. However, in terms of implications to the shape of the p-curve, those forms of selection are completely different. The left-hand side form induces this sharp discontinuity and bunching at a common significance cutoff of 5%. On the other hand, the right-hand side one does not induce any humps or discontinuities. How did I generate these pictures? Well, using what's called thresholding and minimum approach to selection. The thresholding approach to selection refers to the situation when researchers kind of sequentially analyze available specifications and stop as soon as they achieve marginally significant results. That's why we observe those humps and discontinuities. On the other hand, we can think of a situation when researchers are simply analyzing every possible specification they can think of, and then they report the most significant result, or the smallest p-value, hence the name minimum approach. Now, as I just showed you, in terms of implications to the alternative distribution of published results, this is completely different. And it turns out that if we consider all of the tests that currently exist in the literature, those continuity-based tests, monotonicity-based tests, and tests based on the bounds, they can detect the thresholding approach to selection with reasonably high probability if the extent of selection or the fraction of results reported selectively depicted on the horizontal axis here is sufficiently large. However, they're completely useless for detecting the minimum type of selection. As you can see on the right-hand side figure, the power for detecting this kind of alternatives is essentially 0 or equal to size. Now, the method that I propose in this paper provides essentially a strict improvement in power over existing methods for both types of selection, and this improvement can be quite dramatic. For example, for the thresholding extent of selection, type of selection for, let's say, 50% of results reported selectively, we can see that the power improvement can reach up to 3 to 4 times. And for the minimum type of selection, we can also improve the chances of detecting selection by quite a lot, especially given that existing methods are completely useless. So in addition, this paper provides a way of lower bounding this parameter of the extent of selection, which kind of reflects the severity of the problem. I don't talk about this on the slides, but if you're interested, you're welcome to check the paper for that second contribution. I think I'm actually ahead of. I finished earlier than necessary. Thank you.